geometry, we're going over perpendicular bisectors today. And we're going to start with a definition. You've heard the word perpendicular before. You've heard the word bisector before. Now just kind of putting them together. Any thoughts as to what a perpendicular bisector is going to be? Before we do this, I want to make sure my pen works. Okay, there we go. Now we can start. Perpendicular bisector, yeah.
It's something that bisects an angle by 90 degrees.
Okay. That would be an angle bisector. Joey, warning for you. That would be an angle bisector we've talked about before. Perpendicular bisector is similar, but a little bit different.
You were talking to Roland with your hand in front of your face like this. Roland was doing his best to ignore you.
This, and I looked at Abby.
Bro, you were going like this and talking to this.
Perpendicular bisector is a segment, ray, or line that intersects a segment, ray, or line at a 90-degree angle. There's the perpendicular part at its midpoint. So I guess I should change my, hold on, don't write segment, ray, line for this. What? Segment, sorry, whoopsie-doo. Okay. Whoopsie-doo. Bro, I'm sorry. Okay. A segment, ray, line that intersects a segment at a 90-degree angle at its midpoint. So the perpendicular, that's that 90-degree angle part. The bisector part, that is the midpoint part. Okay. Lexi, quickly, yes. So what this looks like here, okay, you've got a segment. We'll draw it onto this section if we're going to fill in the theorem anyway. So you've got a segment here. We'll call its midpoint right about there, give or take. Eyeball that. Okay, I'm not going to prove it.
You have to prove it.
No.
You can't just put it. You can't put it there. You got to prove it.
And so,
Why is that might not be?
morning for you, Rowan. And so the perpendicular bisector, what it does is a segment, ray, line that comes through that mid. Oops. How do you I don't know how to do back on this thing. We'll eyeball. Okay, so the segment, ray, line that intersects that midpoint at a 90-degree angle. Okay, so you've got that situation there. You've got the 90-degree angle. We also know that these two sections are congruent, right? Because that red dot being the midpoint of the segment, that tells us that those two sections are the same length. Our perpendicular bisector comes right down through the middle. And what this theorem tells us that any point that is on the perpendicular bisector is going to be equidistant from the endpoints of the segment. Okay, so that blue point on the perpendicular bisector, if we were to connect that point to the endpoints of the segment, those two segments are going to be the same length. Okay, so in words, if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segments. If a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. What we have here, that point in blue, equidistant from the endpoints. And it really doesn't matter where on the perpendicular bisector that point is. Okay? If we had one down here, that's much closer to the segment than our first point was, right? If we were to connect that point to the endpoints of the segment, okay, these would be congruent sections also. Okay, so it doesn't matter where that point is, any point on the perpendicular bisector is going to create equidistant segments. Equidistant means same distance from. Equidistant. Same distance from. Questions thus far? Okay. The converse, what does the converse do again?
Split. If not this, then
Right, if not that, then this. It flips it. Okay? So if the original theorem says if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segments, if we take the converse of that, it would say if a point is equidistant from the endpoints of a segment, if a point is equidistant from the endpoints of a segment, then what do we know about that point? Arlene?
It's bisected by a perpendicular bisector.
It's on a perpendicular bisector. Then the point is on the, thank you, now I'm aware of it, the perpendicular bisector, right? If a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector. Okay, which makes sense. I mean, if we were to draw a segment over here and put a point out in space, is that point equidistant from the endpoints of the segment? No, it's much closer to the one on the right than it is to the one on the left. Okay? In order for it to be equidistant, right, let's kind of ballpark this so that it's kind of in the middle there. Okay? If this is equidistant from the endpoints of these segments, we know that it is on the perpendicular bisector of the triangle. Mine was a little off, a little bit to the right. But it's essentially the midpoint raised up, right? It's essentially the midpoint of the segment raised or lowered along this vertical line, which is going to keep it equidistant from the endpoints of the segment, because the midpoint is equidistant to start with, right? It's in the middle. If you raise it, it's still going to be equidistant from the end points of the segment, and when you go straight up with it or straight down, you get that right angle there also. Okay, so the perpendicular bisector essentially takes the midpoint of a segment and raises. I'm struggling today. Raises it or lowers it, and what you get is that vertical line going right through the center of the original segment, cutting it at a 90-degree angle, and creating those other segments equidistant from the endpoints of the original. Danny, any question?
Yeah.
Yes.
That has not good language on it, that piece of paper. It says the S word.
Thank you, Damian. I'll investigate it later. Kylie.
does that mean, so if it is a perpendicular bisector, does that mean the triangles that form are always going to be 90 degrees as well?
Okay, Kylie asked a good question. With this whole perpendicular bisector thing, these triangles that were formed, right, by the bisector itself, by the original segment, and the segments you're able to draw in, will they always be right triangles?
Yes.
Yes. Will they always be congruent?
Yes.
Why?
Because it's equidistant.
I didn't know.
Midpoint.
Mid-segment.
Hypotenuse length.
Well, you're right. Okay? The hypotenuse leg, knowing they're right triangles, we have the hypotenuse here, and we have that the original segment, the legs there. They are always going to be right triangles. They will always be congruent, yes, because of HL. Okay? Questions so far? All right. What I want you to do, we're going to pause the video here to kind of talk about what's called the point of concurrency. What I want, well, actually, let's define it first, and then we'll pause the video. The point of concurrency is the point where the three perpendicular bisectors of a triangle meet. Okay? So if you were to take each side of a triangle and construct the perpendicular bisector for that side, and we're to draw it in, they're going to meet somewhere inside of the triangle, yes? Okay? That is called the point of concurrency. Meet. The point where the three perpendicular bisectors of a triangle meet. Question? No. So we're going to pause the video. What I want you to do on a half sheet triangle that I gave you, I've got some protractors, which are not toys, on the folks. I've got some perpendicular or some protractors on that back desk, not toys. I would like you to construct the point of concurrency on the triangle on your sheet. Okay, if you did it correctly, your figure should look something like this. Your point of concurrency should be about in that spot, kind of on the bottom right section of the triangle. Yours might look a little bit different because my triangle is not quite the same as yours. I just traced it based on what you were using. I called it, so it might not be perfect. Then turn around, please. But it should be close to that spot. Okay. Now, folks, the point of concurrency, the definition of it says the point where the three perpendicular bisectors of a triangle meet. So in blue here is the point of concurrency that I have marked there. Okay. Now this point is called the circumcenter. We're going to be talking about three different centers of a triangle based on what we're using. And this first center, called the circumcenter, just by looking at it, how would you justify this being a center of a triangle? Because I mean, if I asked you to put a point in the center of this triangle, you probably wouldn't put it there. Okay. So how is this point a center? Anyone have any guesses? Joey, your hand was up first. You have my marker. Did I leave it sit there? Thank you, Joey.
No, you should have kept it.
Thank you.
It's really like $500 marker.
Arlene.
Since it is the point where.
Good.
Since it is the point where all the three perpendicular bisectors meet, the point should be the point farthest away from all the three sides.
The point furthest away from all three sides.
Should be right there.
And what do you mean by that? Because this point is awfully close to this bottom side of the triangle. So you can say it's the furthest from all three sides. Are you talking like the total distance altogether, or?
Yeah, the total distance.
Okay.
Because it would have been somewhere else. The number of total distance would be lower.
Okay. So usually when we talk about a center, we're talking about like in the middle of something. There's something that is the same distance from, right? The center of a square typically would be, a point in the middle. It's the same distance from all the sides and all the angles and whatever else. Kylie?
I think it's because since all of the perpendicular bisectors are from the middle of the sides, that's the center of all the sides.
Center of the sides, meaning that these segments here coming from the side to the circumcenter would all be the same length, which they don't seem to be. If you did this correctly, the circumcenter is the center of a triangle in that if you were to draw segments to the angles of the triangle, they will all be congruent. Okay? So now go ahead and measure the distance from your circumcenter to each angle and see how close you got. If you plotted this correctly, it should be equidistant from the three angles of the triangle. Okay?
1.5. Hey, we don't want to.
Not a toy. Not a toy.
Not a toy. That's
Oh,
right. Max, talk to Alex later on. He's across the side room.
Wait, what are we measuring?
Again, if you do this correctly, your circumcenter should be equidistant from the three angles of the triangle. So what I did here, folks, is I drew segments from the circumcenter to each angle. Those should all be congruent. Okay? If you want to draw this on your page, that'd probably be a good idea, as close as you can. Again, it's an eyeball thing, ball apart a little bit. Okay?
We're all the same.
That's good.
Stop. I have like no erasers on any of my pencils except this picture. Yeah.
The circumcenter is defined as the point of concurrency of three perpendicular bisectors. Rowan, turn around, please. The point of concurrency of three perpendicular bisectors, and the concurrency, why we care about this, is the circumcenter is equidistant from the angles of a triangle. Okay? The concurrency of perpendicular bisectors of a triangle, the circumcenter is equidistant from the angles of a triangle. So it's a center in that sense. Okay? How this might be applicable, okay? If you wanted to set up something, you know, maybe you have a triangular yard or a triangular playpen for a pet, or you've got a town where you've got, you know, three important landmarks that you can make a triangle with. If you wanted to put something in the center of that, you know, maybe you want to put a statue of the town's founder in the center of, I don't know, school, city hall, and church, or whatever else. And you want to get in the middle of it. How you calculate that is by forming that triangle between the three landmarks and calculating the circumcenter of said triangle. Okay, so it's a way to get the middle of three objects, which would be at the vertex of a triangle. This is the method that you would use to do that. Okay. Questions on this?
So how long would it be on?
Your homework is on page 306, and you are to do 3 to 5, 11 to 14, no, 11 to 16.
Wow.
3 to 5, 11 to 16, and I heard Rowan say he wanted a proof earlier.
We never said proof, we said
Oh, it was Joey? What? Oh, well, Joey asked for it. That's okay.
prove your worthiness.
That is all. Rowan. 3 to 5 and 11 through 16 on page 306. That's how you man. Much appreciated.